In our last lesson, we spoke of limits at infinity. Now we speak of infinite limits. That is, if the limit as x approaches c from the right, if the limit of a function as f approaches c from the right is plus or minus infinity, or the limit of f of x as x approaches c from the left is plus or minus infinity. If either of those is true, then we have a vertical asymptote. And that vertical asymptote is x equals c. All right? Graphically, if x equals c, if either limit goes to infinity or to negative infinity, it doesn't even have to be both, then you have a vertical asymptote there. And c, of course, would not be, in a normal situation, would not be in the domain of the function. So, infinite limits. Now, I want to stress this again. When we say that the limit is plus or minus infinity, we're not saying that the limit actually exists, right? There is no number called infinity. But we are saying that, well, we're describing exactly what the function is doing there, rather than just leaving the amorphous, there's no limit. By saying it goes to infinity or negative infinity, we are describing, and we are in the business of describing when we're talking about functions, analyzing and describing. Okay. Now, in general, you should be aware that when any non-zero number is divided by a number approaching zero, either positive or negative, the result is going to be infinitely large, either positive or negative. Regardless of how small that numerator is, as long as it's not going to zero, if the denominator is, then you are getting infinitely large. So let's just take some limits and evaluate them, okay? And see how functions that look very similar really can behave differently. X squared minus 4. Now we know what we can do here. We know that we can factor, and so we have x minus 2 squared divided by x minus 2 times x plus 2. And what happens here? Well, this will cancel with one of those. As x approaches 2, you've got 0 over 4. That's simply 0. Right? You cannot automatically say that plugging this into the denominator, if that gives you 0, you automatically have a vertical asymptote, because that is not the case. We saw that with our first limit, when what we had was not a vertical asymptote, but simply a hole in the graph. Okay? Something again that looks very similar. Again, we can factor, and we get x minus 2 divided by x minus 2 times x plus 2. But this time what happens? We get a 1 up there. Our limit is now, as x approaches 2, 1/4. Right? So anyway, these things can behave very differently. And now let's see what I was talking about earlier. The limit as x approaches, and we're going to say 2 from the right of x minus 3 divided by x squared minus 4. Now we know that x squared minus 4 is x minus 2 times x plus 2. Okay, as x approaches 2 from the right, and actually we don't even need to factor this. Let's just leave it as x squared minus 4. As x approaches 2 from the right, that means that x is larger than 2. So that x squared is larger than 4. But as x approaches 2, x squared approaches 4 from the right. So what we have in this function, well, in the numerator, what we have, I'll just write it as equals. As x approaches 2, this is approximately negative 1. As x approaches 2 from the right, this is approximately 0, but it's positive. Again, you have a non-zero divided by a number approaching 0. Since the signs are opposite, this is going to be negative. It's going to be negative infinity. Okay, so functions that don't look all that different can behave very differently. This one is the one that at 2 has a vertical asymptote, x equals 2. Okay, so let's take what we did in the last lesson and what we just did here, put them together to analyze one function. Let's say we want to find all the asymptotes of f of x equals, let me write it over here, give myself some room. F of x equals 2 divided by x squared minus 9. Okay, first of all, the degree of the numerator is 0. This is x to the 0. So the degree of the numerator is less than the degree of the denominator. So automatically, we know that there's a horizontal asymptote, y equals 0. Now, clearly 3 and negative 3 are the only values of x that are not in the domain. So if there are vertical asymptotes, those are the only possibilities. Well, we can very easily determine whether those are vertical asymptotes if we take the limit of 2 over x squared minus 9 as x approaches, let's say, 3 from the right. Well, as x approaches 3 from the right, x squared approaches 9, but is greater than 9. This is approaching 0, but is positive. So what we have there, the limit is infinity. Now, I can test the limit as x approaches negative 3 as well, either on the right or the left. The limit as x approaches negative 3, I'll say from the left. Okay, as x approaches negative 3 from the left, the absolute value is greater than 3, so x squared is greater than 9. So again, this is approaching 0 and it's positive, so the limit here is also infinity. If you were really on the ball, you would recognize that what we have here is an even function. And this even function, from way back in our pre-calculus, says that this graph is symmetric across the y-axis. So if we have a vertical asymptote to the right at 3, we must also have a vertical asymptote at negative 3. So we do have two vertical asymptotes here. X equals 3 and x equals negative 3. Oops. Negative 3. So if we were to graph this function, just a rough sketch of the graph even, we could say this, at 3, at negative 3, vertical asymptotes. As x approaches 3 from the right, we're going to infinity, and we also know that long-term behavior, y is approaching 0. We have, as I said, an even function, so on the left, we must have a mirror image. Now, let's get our y-intercept. When x equals 0, we have 2 over negative 9. Now, very small by 9. As x approaches 3 from the left, and that would be very easy to see here. As x approaches 3 from the left, we have 2 divided by a number approaching 0. But the x squared is approaching 9 from the left because the absolute value of x is less than 3. So this is approaching 0, but it's negative. So we're going to negative infinity. And again, since it's an even function, we must be doing the same thing here. And so just a rough sketch of the graph gives us that. And that's all.